So, hi, let's continue. Okay, so in previous class or previous classes, we have studied some mathematical concepts, concepts such as what were they? And they were metric space, okay, denoted by chi, and it gives us a notion of distance function, distance function, okay. Second, a vector space gives us a notion of vectors, and third, dual space that gives, denoted by this, which gives a notion of covectors. Okay, so covectors are also known as one forms, or say dual vectors. Different people call it by different names. So yes, they are also called as covariant vectors, and these are also called as contravariant vectors. So yeah, also one forms are important in the differential geometry. Okay, so important in differential geometry, actually, it is a field of mathematics where you, okay, so like in GR, of course, okay, so this can be generalized, further generalized as P forms, okay, as P forms. And yeah, fourth notion, like vectors are equivalent to contravariant vectors. We just we will see why we call such vectors as contravariant vectors, and they live in vector space. Okay, they live in vector space. And fifth is like yeah, covectors or one forms, whatever you want to call them, or say dual vectors. Okay, dual vectors, I am just confused like what should I write here. There are many names defined for dual vectors. So these vectors are actually covariant vectors, and we will see why they are called such as contravariant and covectors. They live in dual vector space. Okay, so you can call them dual vectors and vectors when you are just considering the definition of vector space and dual vector space. And when you just when you are looking how these components of a vector changes when you change the reference units of these reference axes of these vectors defined in a particular reference frame, and you want to see how they change, then you can just look at these words like contravariant and covariant. And when you just, yeah, you can also define these as covectors. But when you go for differential geometry, then you can call these dual vectors also as one forms. Okay, one forms you can just easily visualize as planes or surfaces, and vectors of course you can visualize as arrows in the space. Okay, so let's understand what are actually the meaning of what is the actual meaning of contravariant and covariance. So let's understand. Suppose we take the contravariant vector. Okay, so contra here means, contra means opposite, oppositely varying. Oh, sorry, opposite, just opposite, because variant means vary actually. So you just consider this as opposite, and contravariant means oppositely varying. Okay, so it means components of vector do vary oppositely oppositely with respect to reference axis. I mean change in reference axis. Okay, let's take an example to understand better. Okay, so consider two frames. One is normal frame, that is in I and j cap. Suppose this is I cap direction, this is j cap direction. Okay, and I have a vector here. Okay, so let's have its components, and suppose there are, it can be divided into four sections. Again, it can be divided into four sections. Okay, so yeah, so you can write this v vector. Suppose this is my v vector as 4 units in I cap plus 4 units in j cap. Now I do some transformation. Okay, some transformation on x-axis, like I just stretched this. Uh, sorry, yeah. So this can be similarly drawn as this. Okay, so and this is my same vector. My vector should not change when I do the transformations on axis. Okay, because it is a geometric object now. So this is my, again, I do not change, I just do not change my y axis, that is my j cap axis. And again, it is of course of 4 units, but I did change my units of, suppose this I cap. So I just increased from, the transformation is, actually the transformation is like I changed I to I cap, which is I just doubled it. Okay, this is my transformation I to I cap, and I just doubled it. Okay, so this is again my same geometric object, same vector, but now the same vector will have a 2 I cap prime plus 4 j cap prime as my components and directions. Now you see, notice, okay, that I uh, what I did is that I doubled my unit vectors, okay, along along x-axis. Okay, so I just doubled it, my unit vectors, but you see that components got halved. Okay, components got halved from 4 to 2. Okay, from 4 to 2, they just got halved. So what did you notice, that so my components, not my components, the components of vectors, actually the components of vectors vary opposite, okay, vary opposite to the the change in the variation in like coordinate axis. Okay, so they vary oppositely. But on the other hand, if I take covariant vectors, what will happen? Let's see. Okay, so let's take covariant covariant. This is O vectors. So this means they co-vary. Okay, vary in similar fashion. Okay, so let's take an example. What do what will vary? The components. Okay, so let's take an example of gradient. Okay, example. Okay, so that it is a gradient. Okay, of f in I cap direction in suppose 1D for simplification. Okay, so simplified case. Now this is my gradient denoted by nabla, and this is my function f. Okay, this is just a gradient, and it just measures that how fast or how much my function is changing when I change my x axis. Okay, when I change my x coordinate. So in this I cap, uh, let's take it my x axis, and this is my f axis. Okay, and I draw some graph like this. Okay, and now I should copy it. Just wait away. So copy paste. Yeah, nice. So let's take mm, yeah, this much and this much. Yeah, okay, and similarly I will take this much here and the same thing here, so that my variation in f axis will not change. Okay, so this is my del f. Again, similarly. Okay, so this is my prime, because after this is after transformation, this is del f. Okay, this much of, and this again I consider like this is my 1 2 3 and 4. Should I consider that? Let's take it something else. Mm, okay, let's take it here one, take it here one. Just it is take 4 distances, and you just take here one and just take here this much. Okay, I know this seems odd, but you can just make it perfectly. So what I did is, like, this is my original I cap, and I just transformed again I just transformed it. Okay, transformed x axis unit vectors like I cap 2 I cap prime is equals to, I just doubled it. Okay, so I cap prime is equals to, I just doubled it. Now you see, this was my del x, and this is my del x prime. Okay, we just see what will happen uh, when I just doubled it. Then what will happen now? Previously this was of 2 units. Now del x prime, you see, is of 1 unit, right? It is only of 1 unit in this axis. Okay, and del f is equals to del f prime. Okay, whatever you take the unit in the f direction, it will remain as same. I have not transformed my f axis. Okay, so now you see that uh, doubling my units of x-axis, the and in the variation in x, variation in x is halved. Okay, it is halved, but the component of gradient is del f by del prime, del x. Okay, how will it transform? It will transform as, like, it is halved, right? So it will be like del x as del x prime, that is equals to del f upon del x by half, right? And this will be equals to twice of del f. Okay, this is my del f prime by del x prime. So my del f by del x has changed to twice of previous one, right? So in this case, you see my my the components of vector covariate covariate, that is doubled, or say increased with increase in unit vectors. Okay, so they covariate. That's why such vectors are called covariant vectors. Okay, that's why such vectors are called covariant vectors. Okay, so let's finish this. So you now understand why they are called contravariant vectors and why they are called covariant vectors. Okay, so for contravariant vectors can be written, or say they are simply called as vectors, and you can just write them as, like, they are vectors. In suppose I am taking in 4 dimensions, I will just write it like this. So it is summation over mu. Okay, that they are like this, and this, and covariant vectors will, these are same vectors, and but they transform oppositely. Okay, okay, I should write it by different notation because they are covectors. So let's write them as not at. Okay, so they can be written as vectors also. So I should write them in opposite way with a different notation. Okay, like this. Okay, so these are co-vectors and these are co-vectors. They live in, okay, living in vector space, vector space, and they living in dual space, two vector of dual spaces. Fine. Okay, but yeah, you just understood that they vary Like the contravariants vary opposite to like covariant vectors, because contravariant vectors do vary like similar to their unit vectors. Sorry, not similar to unit vectors, but opposite to unit vectors. But covariant vectors do vary like similar to their unit vectors. Okay, and that's why they have like we have defined this notation that always the components of contravariant vectors will have an index on the upper position, and similarly this has in the lower position, and similarly for covariant this has the components of covariant vectors are in low stage or say uh, downstairs. Okay, and these are the unit vectors of covariant vectors, also known as one form basis. Okay, so let's move forward and define some interesting thing that Einstein himself like given this notation, and it is called Einstein summation convention. Okay, this will help us convention. Okay, convention. Okay, what is this? So let's write it about it quickly. Okay, so it is a notation. It is a notation convention that implies summation over over a set of indexed indexed terms. Okay, in an expression, thus achieving brevity or say simplicity. Okay, it just simplifies our things, this summation conventions. Okay, let's define what is this convention is. First of all, let's define how many types of indices are. There are two types of indices. Okay, there are okay, not index, it is plural. So yeah, mm, indices, two types of indices. That is, first it's a free index. Okay, and second is my dummy index, also called repeated index. Repeated index. Okay, so what are the rules of Einstein summation convention? The rules are as follows. Rules are as mm, rules are as follows. That is, first, dummy indices. Dummy indices. Okay, these are repeated indices are summed over. Okay, they are summed over or say contracted. Okay, so our previous notation was old notation. Old notation used a sigma. Uh, old notation was for summing the things. was I from suppose this to n. Okay, this is I b I. This is how we do sum uh, over things, right? That's how we used to sum. Now new notation is just remove it, okay, and just write it like this or this. Okay, so this assumes that they are summed over. These indices are summed over because we don't need to keep on like writing this summation sigma again and again. Okay, so we just simplify us this simplifies our calculations. So yeah, again that you know okay, these are my components. Okay, so this is my contra variant vector. Okay, and this with lower indices is my covariant vector, right? You remember it. So suppose an example, I take an example for like dimension 4 n equals to 4 dimensions. Okay, so my summation from 1 to 4 ai, suppose and there is bi, is now in new notation is simply ai bi. Okay, the summation, note that one indices should be like in the lower stage and one should be in the upper stage, okay, upstairs. So this can be written as 1 a1 b1 plus a2 b2 plus a3 b3 plus a4 and b4. You can just like cross it the place of indices. You can write the I indices as the in the upstairs and like this one. So you can also expand this. This just means that we are not using this summation um, notation, and we are just writing this in the this simple form. Okay, so mm, let's yeah, one thing to note is that a quantity, okay, with no free indices, okay, is said to be fully contracted. Fully contracted. Okay, they are said to be fully contracted. If it is not, then it is not fully contracted. Let's say some example. Okay, there is a quantity. mm, Suppose like this I, bi, and cj. So it is not fully contracted. It is not fully contracted. But yeah, of course, this, this, and dj, it is fully contracted. Okay, so there are two indices, two dummy indices in here, and there is a one free indices here. There are two repeated indexes. Okay, uh, I mean the two indices are repeated, not two indices. I mean, I should you understand that this one index is repeated and then one is not repeated. So there is only a single free index. But in the lower expression or lower term, this one, I mean, the all indices are repeated. So all are dumb indices. There is no free indices in the second expression or term. Okay, so yeah, let's go to Second thing, that dummy indices can be relate, relabeled. Yeah, labeled. What is the spelling? I forgot it. Okay, whatever it is, it can be relabeled at will. Will means a choice. Okay, whenever needed, you, I mean, in any expression, if you find like this kind of thing, okay, suppose this is B and J, there are two upper indices, you can just relabel, but not of course J, you can relabel with suppose K. Okay, this is like this. Okay, dummy indices can be relabeled, but not like it should not match with the free indices. Okay, you just take any other indices to relabel it. Okay, so you are free to choose your dummy indices because it, that's why they are called, I mean, that's why they called dummy. Okay, they are not real, or say they do not have any explicit meaning, but free indices have their own power. So third is like, yeah, free indices remain as it is, remain as it is, and are not summed over. Okay, that is of course the third rule that I have already told you. So suppose there is a quantity like this, or say quantity like upper index and this is lower index. Yeah, these are not summed over, these are free indices. So yeah, so number of free indices decides the the rank of your uh, I mean term, this term. Okay, it is actually a tensor. These are actually tensor, but we will introduce it late, uh, later in this course explicitly. Okay, these are tensor, and you can decide like how many free indices you have in a tensor. Okay, so you can decide what is the rank of your tensor term is. So there are two free indices, you can just say that it is a second rank tensor. Okay, so let's do the next thing. An index, okay, should not should not appear more than twice. Okay, this is twice. Mm, how should I write it? Okay, twice in one term. Okay, like this is invalid thing, you cannot write it. Okay, this is also invalid thing. Okay, you cannot write it like this. Okay, of course you cannot write it. So it should appear only twice, not more than that. Or suppose you can uh, choose two different things. Okay, these are tensors, these all are tensors. Okay, so k and I, k. Okay, so these are repeated again more than twice, so this is also not applicable, this is not acceptable. Okay, Now, last one is that the LHS and RHS of any equation must have equal number of free indices. Okay, and must have same position both sides. Okay, let's take an example. Suppose I have a I b j is equals to a I b k, and there is c k, and there is a j. Okay, so here you see that it is of I mean the number of I indices is 1 both sides. Okay, just take both sides, and yeah, j is 1 both sides. Okay, and take these are not free indices, these are dummy indices. Okay, these are dummy indices, repeated indices are dummy indices, so you don't count them. Okay, so you again check the position of I in this in the index is same as upstairs in the upstairs, and the position of j index is again the same downstairs. Okay, so they are in the same position in LHS and RHS, so it is a valid expression, valid equation. Okay, so you can just check that yeah, we have talked also about like metric. Mm, we have earlier, sorry for this mess, let's make it a bit cute. Yeah, there's a summation over mu and nu. Okay, there are two summations. We have already discussed this before, and like this. Okay, so you remember this, right? Where your mu nu and like metric representation was suppose -1 -1 -1 0 0 0. This was your Lorentz metric, right? So you can just rewrite this as minus dx uh, 0 squared plus dx1 squared plus dx2 squared plus dx3 squared, right? Where your you can consider your x0 is ct. If it is ct, then you will get this kind of Minkowski time interval. Okay, this is my x. Suppose take my x1 x, x2 as y, x3 as z, then you can just rewrite that. Of course, you know this, right? So yeah, let's remove it, y and z. Okay, so but in Einstein summation, this can be written simply as ds squared as eta mu nu and this and this. Notice that always in the sum, one dummy indices should be downstairs and one on the upstairs. Okay, then it is considered as the sum. This is our convention. Okay, you cannot take like this as this is an invalid thing. Okay, these are not, this is not as invalid. Okay, Dummy indices in summation should always be in opposite position. Okay, so you just check things. Okay, so let's do some examples now. Just we I have to cover uh, just one topic more after this question. Okay, there's a question here. It's a small topic, don't worry. So this, one of them which one of them don't make sense? Okay, you have to write this and restore the sums on dummy, okay, indices. Okay, so let me give you some examples. Like first one is xi cap equals to a I cap j cap b j cap, sorry, not cap, this is x, okay, and k indices. This is I equals to a j k, this is k l, this is l, okay, okay, this is I indices, right? Yeah. Secondly, this is j a I k b k k c k and j. Fourth one is d I j is equals to a I k b k l c l j. Okay, another one is a I j x j plus b I k x k. Okay, and x I is equals to this plus b I j x j. Okay, and b I j is equals to a I k b k l c l I. So remember, when you are writing any tensor like this, I mean, don't worry that what is the tensor and all things, but you just remember, we will read this, what is a tensor, but you just remember if you are writing any indices, suppose this is here, then below it, it should be a vacant place. Okay, then you should write any other indices, and above it, it should be a vacant place. Okay, so that's why you can write like this things and like this. So there is a vacant place both here and there. So you consider it as a slot. Okay, you can consider these are as slots. So if one slot is filled by something, then the other should be filled by something, and both the positions should be like occupied by a single thing. Okay, like this. So just forget it. Okay, so not forget it, but I mean just don't forget this. Yeah, so yeah, take the first example. You see the number of free indices are only one. Okay, that is I. Okay, both j and k are repeated and are summed over. Okay, so how many free indices are there? Only one, and there are two dummy indices. Okay, so there is how many summations will run on? There are two summations on j and k. Okay, and of course, what was our other rules? Our other rules were like you can relabel your dummy indices, but of course not the already given indices. You can relabel your j, like suppose I can relabel it to L. Okay. The it will not affect my expression. So I can write A I L L K K, so it will not affect. Or you can just replace your K with L or some other factors, other indices, it will not affect. So dummy indices can be replaced with any relabeled. Okay, but you cannot, yeah, of course, in the expression you can relabel your uh, free indices, but not in the particular term. Okay. So I mean, if suppose there is a, yeah, you cannot relabel it here by retaining this as I. You cannot relabel this as J, because in both sides the number of free indices should be equal then. Okay, so this is a valid thing. Now let's come to this one. So this is I, this is J, and these are both same thing. They have relabeled it. Okay, so this is valid, but their number of indices, free indices, are same but different. Okay, I mean the number of indices, not only number of indices, but the indices should be same on both sides. So same number of, I must have seen, I mean, must have same equal number of free indices, and must be same both sides. Must be okay, and must have same positions both sides. Okay, so that is that I should consider. So this is a wrong thing, because we do not have I in this term here. Now next come to this one. So there are more than like two dummy indices only, according to the second rule. Not second, yeah, the fourth one. The index should not appear more than twice in one term. So this is again a wrong thing, because there are four terms, four indices of same thing, same indices. Now next is this one. So yeah, the position is same, position is same, they are ठीक है ये, it's okay. So it's well and good. You just check it. These are okay, these are okay. They are just, you can just relabel it. Okay, just okay, in this second one they have relabeled. Okay, so it is also a valid thing. And you can just check that by this equation you can jump to this equation by relabeling this k. And now you can, here you cannot take common out like xj from this expression, but now after relabeling you can take this xj common out from this both terms. Okay, so the positioning is correct, and the mean indices are all correct, and number of uh, there is some issue. Okay, yeah. So of course, just there can be a confusion here. Of course, I got it. So LHS and RHS of any equation must have equal number of. This is a wrong thing actually. I mean each term in each indices in each term. Okay, so yeah, now it is valid. So there are two terms here in the RHS. So there should be in each term there should be one I uh, index, and there is of course in this also there is one I, one I, one I. So it is a valid thing. Okay. So previously it was wrong, because you may consider it like there are two indices here and one. So it is wrong, but it is not wrong. In each separate terms there should be one index, free index, if the LHS has one index. Okay, so this is correct, and this is also correct. Yeah, there's no issue. And in this one, they are repeated, but yeah, of course, there is no j, and they have there are, you can see that here it is j and here it is I, so it is not correct. So you can just do this. Okay, so try these. You can find more on the web, say textbooks. So this things will help us more. Einstein summation convention is very useful in future course, in future classes, in understanding uh, relativity easier. So let's finish one thing, okay, before we end the class. That is displacement for vector, or say for displacement. It is a four vector. Okay, so four vectors just are just vectors, or say elements living in a vector space of dimension 4. Okay, so this is a 4 vector, and it is a particular type of 4 vector, that is displacement vector. And how do we denote it? Let's do this. Just like three vectors, we can define a displacement vector like this is in the space time. Okay, so this is my time axis, this is my space axis. Okay, so in the space axis, how will you define the s prime frame? We call it, it will be like this: s prime frame, this is ct prime, okay, and this is x prime. Okay, just consider of 2 points here, and what these 2 points represent in this ct graph, tx graph. These represent events. Points are equivalent to events, right? So just make an arrow here. Remember, we have studied that all the vectors can be represented by an arrow physically, geometrically. Okay, this is an arrow, and this is again an arrow, and this is again. Okay, so this is A, this is B, suppose point. So this is a displacement vector A, this is a displacement vector B, this is a displacement vector AB. Okay, so you can just see, like from triangle law, that this vector actually equals to this vector plus this vector from triangle thing, and the law of addition of vectors, and you can just see that the displacement vector is given by this minus this thing, right? So they are all geometric objects. So just like three vectors, they are, I mean, what, two, four vectors. Four vectors are also are also geometric objects. So what does this mean? You remember what is a geometric object? So they do not depend on any representation. I mean, the general properties of these vectors do not depend on the which on I mean, from which frame you are defining it. Okay, so but it may have different representations in that particular frame, but actually the intrinsic properties, just like magnitude of an arrow or a direction, overall direction, do not depends on actually the frame, but in that particular frame it may have a representation. Okay, so this is the thing. So yeah, so it is a geometric object means this vector AB in S frame, suppose in S frame can be written, I mean, let's not write summations from now because we have introduced Einstein summation convention. So this is a vector. Okay, uh, I mean, I should not write it a single vector. This is a four vector, so I should write it like this. This is a four vector now in four dimensions. Okay, in four dimensions because there are four lines creating it. So this is a four vector, and for a three vector we have three lines. So this is my notation. You will not find this in any textbook. So yeah, this is a four vector. You can write it like x mu, and in any particular representation, that is, it should be like this, and there should be a cap. Yeah, now it is fine. It is a four vector. Why it is a four vector? Because mu runs from 0, 1, 2, and 3. There are four dimensions, and it represents my CT coordinate, and this one represents x, y, and z. Okay, so this is how there is a summation. These are dummy indices, so they are summed over. So we do not have to include the this particular uh, sign, that is of sigma. Okay, so this is the thing. So since it is a geometric object, so it should be same in the prime coordinate also. Let's denote it by primed indices. Okay, let's denote it by prime indices, and let's make this relabel it with some different indices, that is alpha. Okay, so let's rewrite this in proper sense, that in S prime frame the same geometric object have different representation and given by this thing. Okay, so this is the thing. Now, how do you, what does this mean actually? Okay, I want to just clarify one thing before we go first forward, that in my previous classes I have just done a mistake. You go here, yeah, here. There is a mistake here. How? Let's see. So I cannot write this like this. Not a good notation. Okay, you just better write it like this only. R, cap, R prime, this and R. This is correct. Why? Because this equation, this notation actually tells you that there is a vector, okay, there is a coordinate vector which I have defined like this, and it has transformed to another vector. It has transformed to a different vector. Okay, but in our theory, we are not transforming the vector, because the sense of geometric object will not retain them. Uh, Since the vectors are geometric object, so they should not differ by any transformation matrix. Okay, so what is actually transforming are the components. Okay, these are the components, or say the coordinates uh, of x. So I should not define like this, so this is not a correct sign. So better you write this as like r prime is equals to this is a matrix now. So this is, we should write this, and this is a wrong notation. Okay, not a good notation. Just remember it. Why? Just you just see that there are two types of things. Okay, let me write in the things. Okay, so you just correct it in the, I suppose it is in the sixth. Yeah, you just correct it here also. You don't write it like this. This is a matrix notation now. Let me explain it. Well, that is correct. Yeah, yeah. Come to this thing. So note, sorry, yeah, note that previously we wrote previously we wrote Lorentz transformations as prime is equals to, this is Lorentz transformation matrix. Okay, this as this is a wrong thing, wrong notation. Okay, why? You just check it that what we are doing, what we are doing are actually is actually called is actually called passive transformations. Passive transformations. Okay, in contrast with active transformations. Okay, so what is a active transformation and a passive transformation? You just see that there is an vector here, and you just apply a rotation matrix. Suppose apply a rotation, and this was your previous vector. You apply a rotation, and it will go to a different vector. Okay, it will go to a different vector, and the axis remained same throughout this transformations. Okay, this is an active transformation. But what we are doing, actually we are just changing the frames itself, we are changing the coordinate axis itself. Okay, so my coordinate axes are now changed. Suppose this is, that's why these are called coordinate transformations. These are also coordinate transformations. Okay, but the components will change. Okay, but the unit vectors will not change actually. uh, Unit vectors will change or not? I mean, this frame of the frame is same. So yeah, unit vector should not change, I guess. We will check it to any other thing. But here there is I prime, there, sorry, j prime, this is j cap, this is suppose I cap, this is j prime, this not, this is I prime. Okay, so we are just defining, we are keeping the point same. Okay, the here the point is different, axes are same. Okay, mm, yeah, axes are same, but the components will change. Okay, the components will change, and keep we take this in I cap and j cap only. So yes, the vectors unit vectors won't change. So this is a passive transformation. Here the vector is same, the point is same, point remains same. but axis changes. Okay, so a vector remains same always. So this is a geometric object. Its intrinsic property will remain same, but you can like define it or say see it, observe it from a different reference frames. Okay, this is a prime frame, S prime frame, and this is a S frame. So this is a passive transformation. So this after this you should not write this. You should not write this. This is wrong. So you should always write this in passive transformations that they are always equal. Okay, in passive transformations. All coordinate transformations are passive transformations. Okay, we are not changing the point. We are not changing the vector. So as per this rule, we just come to our early case. Okay, suppose I take this as equation A. Okay, how much time is? So I should end this, and we will continue in the next class. Okay, okay, it's fine. Continue in the next class. Thank you.